This lab looks at one of the most common structural components in the built environment. You see trusses everywhere, from world-famous structures to local buildings and bridges, and even, more than likely, in the roof above your head. Why are trusses so common? With struts running in X and Y directions, they are strong, and the diagonal members add stability as shown in this video. The marshmallows hold the sticks together, but they don't really stop them from bending relative to each other. And in that regard, they're not unlike the pin joints in the truss in the lab that you'll be doing. When a weight is placed on the box structure, it collapses quite easily. However, when the diagonal struts are added, the structure is stable against collapse and capable of supporting quite a large load. The Aviva Stadium in Dublin is a standout example of the use of trusses. There are 3 sets of different truss types running in a large horseshoe construction which supports a roof that covers the entire crowd without obstructing anyone's view. It's an amazing and beautiful structure built out of trusses. But how would you ever begin to design something like this? Well, the starting point is to be able to quantify the forces on any individual truss within that structure, and that is what we'll be doing in this lab, both calculating and measuring these forces. As you can see, we have 2 trusses in the lab apparatus, not one, joined together so that they don't fall over. So we only look at one of these trusses, and whatever load is applied, we just halve it and say that half of that load is acting on that individual truss. Seen from the side here, the truss structure is as follows, and it's quite easy to draw in the external forces acting on this. As I said, half of the weight that's applied and the reaction forces at these points. It's important to note that the reactions are slightly different here. In the center, it's just a point reaction that can resist force in the vertical, but in the horizontal it's free to slide, whereas at this point here, it's sellotaped to the desk, so it resists motion in both the horizontal and the vertical. So it's quite easy to calculate the external forces at these reactions by just doing sum of forces and moments about a point. But what about the internal forces? Well, the first thing to realize is we make one key assumption in this kind of analysis. We assume that the struts themselves are weightless. Why do we do this? The key thing to note is that the applied weight, the weight that's hanging from the truss, is much greater than the weights of the individual struts. So it simplifies the force diagram as all forces act directly along those strut members. So when you're doing this analysis, you just assume that the forces are either tension or compression. And at the end, if you get a negative answer, you know that your assumption was incorrect and you just flip the direction of those arrows around. So how do we calculate these forces? Well, what we do is look at specific points one at a time. So looking at that point, if we call it A, we know that the forces at A must balance out to 0 because it's not moving. So by naming the other points in the structure, we can name our forces, resolve them, and with moments and sums of forces, by taking these analyses at different points, we can find out all of the unknown forces. Having calculated the forces, how do we actually measure them? Well, this is a little bit more tricky. You can't measure a force without actually somehow being inside that strut member to feel the force. So what we do is we break open the strut, put a force sensor in line with the strut so that it's measuring the force through that strut, and then we measure it directly at different points in the structure, as you can see, and get those direct readings of the force. When doing the lab, it's important to zero the sensors before you take readings each time. This is like zeroing a weighing scales at home before you use it, but you have to do it directly before each measurement as these readings drift. When you've measured the readings, compare them with the ones you've calculated and ask the question why they might be different. What assumptions might have led to those differences, or what inaccuracies in the way the experiment was carried out.